A homopolar motor is an electric motor that uses direct current to generate rotation. Here's a setup of the homopolar motor that we used in our experiment. It consists of a battery, a screw, a magnet, and a wire. The battery provides the voltage, the wire completes the circuit allowing current to flow, the screw gives the magnet a point to spin on, and the magnet supplies a magnetic dipole. One of the elements we looked at was the direction the motor would spin in. This also serves as a brief overview on how the simple homopolar motor works. The diagram shows an image of another simple homopolar motor. Because current always flows from a higher potential to a lower potential, the current's direction will run from the top of the battery to the bottom. This particular magnet is in the north-south orientation, as indicated by the direction of its magnetic dipole. According to the Lorentz force law, the points where the magnetic field lines intersect with the current will produce a magnetic force in the direction orthogonal to both of the other directions. This can be determined using the right-hand rule. This force on the wire is what causes the wire's rotation. We used a simple homopolar motor to deduce the orientation of our magnets.
The direction of our setup and the direction of the resulting force is shown here on the left. Next, we compared the theoretical and experimental angular acceleration of our homopolar motor. We modeled the direction of the current with the vector dl, which goes from the top of the magnet where the magnet attaches to the screw to the side of the magnet where the wire touches the magnet. dl is composed of two components, negative dz in the vertical or z-hat direction and dr in the radial or r-hat direction. As we previously determined, the magnetic field points up through the magnet. We plug these values into the Lorentz force law to find the change in force on the magnet. We know that the change in torque is the r vector crossed with the change in force vector. We plugged in and integrated the appropriate values to find the torque of the system. Angular acceleration is torque divided by moment of inertia. Plugging in the values we found, we determined that the angular acceleration is equal to the current times the magnetic field all over mass. Our AA battery provided 1.5 volts and the total resistance of the system came out to 1.15 ohms. Using Ohm's law, we found that the current through the system was approximately 1.3 amps. The mass of the spinning portion of our homopolar motor came out to 0.0044 kilograms. We assumed that the grade of our magnet was N42 with a residual flux density of 1.31 teslas. This was not an unreasonable assumption, as the range of common neodymium magnets only span from 1.1 to 1.5 teslas. We calculated the magnetic moment with the dimensions of the magnet. We then used that to find the magnetic dipole. For the purpose of our calculation, we modeled the magnetic dipole as a point inside the magnet, so the radius is the radius of the magnet. Otherwise, the magnetic field would go to infinity. In addition, the wire was level with the center of the magnet, so the angle is 0. Our magnetic dipole was, interestingly enough, equal to the residual flux density at 1.31 teslas. With values for the current, magnetic field, and mass, we found that the angular acceleration of our homopolar motor was 389 radians per second squared.
We used this video to gather experimental data to compare with our calculated results. Our video is shot at 30 frames per second, meaning that approximately 33 milliseconds passes between each frame. By playing the video back frame by frame, we were able to count the number of frames between the first 3 full rotations, and thus estimate the time it took to complete each of the first 3 rotations. We were only able to count for the first 3 because following that the magnet was spinning too fast for the frames to keep up with. Once we had the time per rotation, we could find the angular velocity at the end of each rotation, from which we could find the angular acceleration, as angular acceleration is simply the change in angular velocity over the change in time. This table shows the values we recorded from experimentation. To find angular velocity, we divided 2 pi radians, which is 1 revolution, by the time between each full revolution. This red line on this graph represents angular acceleration over time in our system. For the first revolution, it's clear that angular acceleration is relatively low. For the next 2 rotations, however, it increases sharply but appears to begin leveling out. The blue line represents angular velocity, which is increasing and does not appear to begin to level out.
So what can we conclude from our calculation and experiment? There were 3 major assumptions we made that would not hold in the real world. In our calculations, we did not consider frictional forces since we did not know the frictional coefficients. However, we know there was significant friction since pressing the wire on the magnet just slightly harder caused the magnet to stop spinning. We also modeled the magnetic dipole as a point inside the magnet to prevent the magnetic field from going to infinity. For our experiment, we found the angular acceleration by counting frames, which became difficult when the magnet began to spin faster. It seemed to stay constant after the first 3 rotations that we measured, so we assumed that the angular acceleration leveled off at that point. Although there is a clear difference between our calculated and experimental values, they are within the same order of magnitude, and we believe that this difference can be accounted for by the frictional forces we left out of our calculations.